All right, Calculus 12.0. So today, going to be taking a look at graphing of functions, and so we're going to be using calculus techniques in order to do that. So right off the top, let's talk about first derivative. So we've already done a little bit of an exploration into extreme values. So the idea of extreme values, we said that Fermat's theorem said if the derivative exists at something that could be an extreme value, then that derivative is going to be zero. Now, that derivative being zero does not guarantee that the value that we're looking at is going to be a local maximum or a local minimum. It could be something that's known as an inflection point or some sort of a saddle point, depending on the language that you're using. But the idea is that it will give us an idea of things that we are hoping to find and be able to describe graphically. So when you do a first derivative, you are going to look for critical numbers. You are going to look for places where the derivative has either a value of 0 or does not exist. Most of the time, we're going to be looking at pretty functions. So these pretty functions are going to not have a ton of places that are interesting that have a derivative of do not exist. That usually is something that goes along with an asymptote. Or if you have a piecewise function, then of course you can have derivatives that do not exist because of the slope being different coming in from the two sides. So we're going to look for those critical numbers like we talked about in extreme values. Now, probably the important part of this is knowing what those critical numbers actually are. So I'm going to talk about the first derivative test and the second derivative test. The first derivative test, if you take the function that you have found the derivative of and you list the critical numbers on a number line. So we're going to put critical numbers. Now, you don't have to list them graphically on a number line. That's optional, but it's not a bad idea. Some way to organize your information. So if I found one here, here, and here, what the first derivative test does is it tests what the sign of the derivative would be around your critical numbers. Because your critical numbers are places where your derivative the derivative sign could change. So if we think about what a local maximum is, a local maximum is when you have a function and it goes up and then it's going to come back down because nearby that value is the highest possible value that you can reach. So think about the slopes coming into that. So the slopes are positive coming up and they're negative coming down. There are no other options for it to be a local maximum. So because of that, we can kind of test and get an idea of what these things should be behaving like. So what we test, as I said, was test f prime x in between your critical numbers. So for instance, if I just have these three critical numbers, I want to test one of them on this interval, one on this interval, one on this interval, and one on this interval in terms of the first derivative. So let's just talk about what this may look like. And we'll use an example later on where we can kind of get an idea of what this should actually end up looking like. So if I took, for instance, and found that the derivative was positive, negative, positive, positive, what would that mean if the first derivative was positive, negative, positive, positive? Well, first of all, like we just said a few moments ago, if you had values for the first derivative, which are the slope, that are positive coming into a value and negative coming out of a value, then that's going to give you this idea of a local maximum. If instead, the next transition that we have is we have negative values coming in and positive values coming out. So you have one of these like bowl things going on where you have negative and then positive. And so that's going to be a local minimum. However, the last one can happen still. So just because the derivative becomes 0 doesn't mean it has to transition. You know this from graphing, for instance, a parabola that has a vertex on the x-axis. Just because you have an x-intercept doesn't mean it has to cross through the x-axis. It could bounce off of the x-axis. So in the case of the numbers becoming 0 for the critical number, or D&E, but we'll kind of go with the simple examples here. If this was a 0 at this particular location, it doesn't mean that the signs of these two automatically have to be different. So if you have, for instance, positive slopes coming into it and it flattens out to give you 0, but you have positive slopes coming out of it afterwards, you could have this cool little squiggle that goes on, kind of like a tan function or just an x cubed function, where they kind of flatten right out, but then they grow again on the other side. And that's going to not give us a local maximum or a local minimum. But we'll see something that we can say about that particular value coming up. But it doesn't give us a local extrema. So that would be the first derivative test. You basically have already found your critical numbers. You take the first derivative of your function. You test that first derivative's result, or the actual function that is the first derivative, at each interval that has been created by your critical numbers when you write them down. So critical numbers should also include values where the derivative does not exist. So if you have, for instance, an asymptote on your graph, there is a possibility that on either side of your asymptote, it basically does not, it flips the direction of the slope. So you have seen with the reciprocal functions in pre-cal B, or rational functions, where you have an asymptote. Sometimes coming into the asymptote, they curve like this. So that would be basically curving down and having a negative slope. And then maybe on the other side, they come up like this, and so that would be positive slope. And so there was a transition there from negative slope to positive slope, even though there is no solvable number for the derivative there. So it can happen where the derivative does not exist either. So if you did have places on your original function where you had a domain problem, you would also have to record those as your set of critical numbers on your number line, keep track of them, and test your derivative on either side of those as well. So that is, as I said, first derivative test. Second derivative test is very similar. You're basically going to be looking at your set of critical numbers that occur for your original function f of x, but instead of finding the first derivative and using that to test what's going on, we're going to use the second derivative and test what's going on there. And so the second derivative is interesting because that's something we actually have not really discussed yet, which is kind of getting down further into what's going on there. But I'm going to have to cheat it forward now because I forgot I needed to use it to discuss the results of the second derivative test. So the second derivative is telling you how fast your change is changing. So if we think about the first derivative, that is how fast a function changes, the slope. But it's how fast your slope changes is what we call the second derivative. So you can have, for instance, if I have a positive slope and that positive slope is changing to become more positive, it may look like that. If I have a positive slope, but that positive slope is changing to become more negative, or flatten out basically, and maybe eventually become negative. That's my curvature is a little bit funky. There's an inflection point there. I actually, that's gonna bug me, so I'm gonna back it up the train here and go like this, positive slope, and kind of flatten out like that. So the idea is that the change of slopes creates curves, or curvature, that we are going to label the certain types of curvature like this by using the term concavity. So there are two types of concavity, and I usually talk about them a little bit in Physics 11. So if you were unlucky enough to have me for Physics 11, then you may remember this sort of thing because I have a very this is my like go-to when I talk about this sort of thing. We have happy curves and we have sad curves. So what do I mean by that? Well, as you can tell here, this is a positive slope rate here that is increasing. That is, if you were to extend that particular shape, it would look like a happy or smiling face. A happy or smiling face type of curvature, oh, oops, I thought that was a highlighter, that occurs specifically when you have a positive second derivative. And the reason why is because the change, whatever change is going on, the change in your slope values are positive changes. So if you have negative slope values, they become less negative. If you have positive slope values, they become more positive. So at the beginning here, if I'm taking a look at this, these are very negative slope values, and they're going to decrease how negative they are, and they're actually going to flatten out and become zero, but then they become slightly positive and then become very positive as you go out the other side. This is a positive change in the slope, whether it's slowing down a negative or speeding up a positive, same sort of idea. This is positive concavity, or positive second derivative, I guess I should say. Positive second derivative, and I usually refer to this as being concave up. You can also use concave and convex, concave being this one, I believe, and convex being the other. I don't use that language very often, so you might want to take a look at that if you think you'd prefer to use concave and convex versus concave up and concave down. For me, positive up links really nicely. It's seen as being a pretty standard set of English terminology to go along with that, so I'm pretty happy with concave up, concave down. So I'm going to leave it at that, and then I'm going to draw the other type of curve, which is an unhappy face. So for me, happy face is positive, sad face is negative, and it goes along with negative second derivative as well as the terminology concave down. So if I were to go along and kind of say, oh, this is a really high positive slope and it's becoming less positive and becomes zero and it becomes a little bit negative and it becomes a lot negative later on. Same idea. So you have a slope that's transitioning to become more and more negative as you go along. So this is the second derivative. Now, when I refer to the second derivative test, we need to have this idea of concavity and what the second derivative describes. But instead of testing on the intervals, you could test what's going on at this point. Because if we could show that the second derivative at that particular point was negative, then that means it's part of an unhappy face. So I'm going to give you a guess first, and you can pause the video if you want. If you were to have an unhappy curve that looks like this, and you knew that this was a critical number in the middle, can you say anything about that critical number if you know that the concavity, as you go through that critical number, is concave down so that it looks like this? And the answer to that is yes, you can, actually, because if it was concave down, and you know that it basically flattens out to give you that nice zero slope, because that's why that critical number came up that way, then you would be able to say that that is a local maximum. Same thing with the local minimum. So if you have one of the bowl shapes instead, and you were to transition along towards that point and you knew that it was at the bottom of a bowl, well, that has to be a local minimum if that's one of your critical numbers there as well. So you can test the second derivative at those points. And one of the things is the second derivative won't work if the first derivative doesn't, like if the function doesn't exist there, you can't come up with a derivative and you can't come up with a second derivative. So if this thing was had a domain issue at that point, you're not going to get a positive or negative second derivative and then kind of by mistake bump into this or this when you're not even supposed to because it was an asymptote. It won't happen, so it won't be an issue. So this would actually correspond to the same set of information as what's on either side of the critical number up there, if this was the same function. So knowing that the first derivative is positive then negative is basically the same information as testing at the point and saying it is concave down. Same thing here. If this was transitioning between negative and positive for your first derivative, then that would look kind of like this. So it would be coming down and then it would be coming back up, and you would have a concave up or positive second derivative here. So these are the signs of the second derivative. Now, this is going to, if you were to find something like, for instance, 0, or you could potentially have these kind of interesting things where they wobble instead. And so the presence of a 0 second derivative is a possible inflection point. Now, what we would basically do is you would test to see, does the concavity change on either side of this point? And so if I gave you a little bit of an example of what that might look like, we said earlier that it would look like a Tanner cubic. So if I had this thing come over and flatten right out and then get steeper on the other side, kind of like this, then what we could say is in this area right here, we had concave down going into it, concave up coming out of it. Its first derivative is going to be 0, which means its second derivative is also going to be 0. So we would find that this has a 0 second derivative, but it also is, oh no, sorry, 0 first derivative doesn't necessarily mean 0 second. It does in this case, but that's crappy for me to say because it is not true at all. So just bear with me for that one. Skip over. Forgive me for what I said. So we in this case, but not generally. So we have this thing coming in, flattens out, gets larger on the other side. And so we get this idea of first derivative of 0, also second derivative ends up being 0, because the only way for you to switch between this one, which is concave down, and this one, which is concave up over here, is for you to, which means second derivative less than 0 and second derivative greater than 0, so it has to be second derivative equal to 0 at that particular middle section. So this is what we call an inflection point. So inflection points are times where you transition between concave up to concave down or concave down to concave up. If you notice on my down there, I say POI. POI is the lazy way to say point of inflection. So if you have an inflection going on in your graph and somebody asks you for a POI or point of inflection, you're going to list the x comma y coordinates of that point that you found. So this is basically the set of calculus tools that we are going to take and apply in order to be able to graph things a little more carefully than we used to. So this is going to be a little bit nasty, but this is what we are now expected to do in terms of graphing. We are expected to be able to come up with, basically, I'm going to skip that for a second, this set of information. Domain, not calculus. Intercepts, not calculus. And we're not going to do fancy ones that involve having to use Newton's method or something like that. So just not calculus yet. Symmetry, odd, even, neither, not calculus. Find all asymptotes, generally not calculus, although you can use limits to describe asymptotes, so you could argue that it's hand in hand with calculus, and especially because you can evaluate some limits using L'Hopital's rule, blah, blah, blah. So that one maybe you could if you wanted to. For E, find intervals of increase and decrease. That is your first calculus thing, because that requires you to take the first derivative of what's going on and then be able to state that your first derivative is positive when the function increases. Your first derivative is negative when the function decreases. So you can find all the places where you have critical numbers, and then you can test the first derivative on each of those intervals, which basically sets you up for a first derivative test already. So in doing the intervals of increase or decrease, you are already kind of forced into the setup anyway for your first derivative test. We're going to identify any local or absolute max or minimum values. Generally, you might circle back to do the absolute part. You're definitely going to do the local part as you go through and get an idea of how it looks. But you might circle back, as I said, to do the absolute max or minimum after you have a little bit of a better idea of how the function behaves out towards infinity and just kind of get a little sketch first. There's nothing wrong with that. Because really your absolute is a discussion of either endpoint conditions or whichever local ended up being the lowest that your range doesn't go down below, or vice versa, being the highest that your range does not go up above. Then we're going to be finding concavity. So that's the second derivative. You find out where that second derivative is a negative or interval, negative or positive in between your critical numbers, and where your second derivative, where your second derivative is either equal to 0 or does not exist. So not necessarily critical numbers. Second derivative being equal to 0 or the second derivative not existing. You put them on a number line, you do your comparison, and you'll be able to tell where this thing is concave up or concave down, because in order to transition concave up to concave down, you have to go through either 0 or potentially a place where it does not exist. And that's the hard one to remember, is that does not exist. So we'll probably get used to that as you do some examples and work on it. Finding points of inflection. So once you're pretty sure that you have found places where your derivative is actually 0 at that second derivative is 0 at that location, then you find the y value at that location, and it is the point of inflection. Then you take the thing and you graph it. Lots of fun. So what I want to show you is that basically graphs are 4 pieces. Unless they're linear, which would be not going to happen really in the stuff that we're looking at, because it's actually weird for something to be linear in the middle. You need it really to be piecewise to follow something like that. Excuse me for my yawn. So you'd have these 4 pieces, and those are basically all you ever need to graph. So those 4 pieces are split up into 4 categories. You either have things that are positive first derivative, which are your first column right there. And so positive first derivative means you're going up like this or up like that. Don't know which one, but both of them would apply. Negative first derivative would mean that you're coming down like this or maybe down like that. And either one of those would be okay cases. But each one of those cases can be split up by looking at the second derivative, which is the concavity. So you are also, if you notice, this is your unhappy face down here because it's concave down. This is your happy face, but it's written the other way around. So you'd have your concave up pieces. So if you are concave up and increasing, you can only look like this piece does right here. If you are concave down and decreasing, you can only look like this piece here. Now, technically, you can look like any part of this piece. So it doesn't have to be like the full thing. It just has to have a piece of this sort of shape to it. So every time we're connecting these important points that we find, you're going to be connecting them using one of these 4 pieces. And so once you have those pieces and you have things like intercepts and asymptotes, then you can do a pretty good job of getting a nice tidy graph. So what I'm going to do is I'm actually going to throw this up here, and I'm going to do a very simple one just to get us started, and then I'm going to leave it at that and give you some practice And then I'll probably do a video of a couple more examples later on this week. But let's go ahead and do a nice tidy one to start. So if I said f of x is equal to x cubed minus x plus 2, let's say. No, I'm not going to do that. I'm actually going to keep it real tidy for my my intercepts. So I'm going to be really cheesy and just go with the x cubed minus x function. All right, so first of all, find the domain. This thing is a polynomial, so its domain is just x such that x is an element of the real number system. So that's all I have to put for the domain, and the reasoning for it, just because it's polynomial, is fine. B, find the intercepts. So intercepts occur when the function has a value of 0. So this thing has a value of 0. I'm going to factor the x out, and notice that that leaves us with a difference of squares. So our difference of squares is going to factor into x plus 1 and x minus 1. Since we have three factors that when multiplied give us 0, you would have either that your x is equal to 0, your x is equal to minus 1, or your x is equal to positive 1 as being your three possible, or three intercepts that we have here. So probably because it's intercepts, I'll just list them as being 0, 0, -1, 0, and 1, 0. So those are going to be three important points that occur on the graph that we're going to create. Asymptotes, it's polynomial, so it doesn't have any asymptotes. You could talk about end behavior if you wanted to. So the end behavior here, since it's a positive cubic, I'm going to remember the mirrored image here. It's going to be going from quadrant 3 down here to quadrant 1 up here in terms of the shape. So the, I mean, you could kind of use that as part of what you were thinking about, but I'm just going to say that for the asymptotes, don't have to worry about those, none. I did skip over the symmetry, which is sad because this actually does have some nice symmetry. So if you forget how to test symmetry, basically, you just take the original function and you replace the argument with negative x instead of positive x. When you do that, we're just going to evaluate what that does to this particular function. So in this case, it's going to give me negative x cubed. So it's negative times a negative times a negative, leaves us with a negative. And we'd have plus x, which is actually the same thing as if I factor the negative out. I have negative, and then this part right here is the same thing I started with. So what this says is that if I change the argument to be the negative of what it used to be, so the opposite side in terms of flipping like this, then I actually get the same function that I did before, except for everything is flipped sign-wise. What that equates to is something that we call an odd function. And so if you forget what odd functions look like, they basically, even functions are flips like this, and odd functions are flips like this and this. So it's kind of got this nice double reflection symmetry, if you wish. And so in this case, we'll see that symmetry. You don't really have to know how it looks. What's nice is if we really wanted to be lazy, if you have even symmetry or odd symmetry, you only have to do half of the domain when you're figuring out what's going on, or half of the domain when you're using test values, because you don't need to assess what the other half is going to do, because it's just going to be either the same values if you have an even function or the opposite sign values if you have an odd function. I would say that actually testing the values helps give you a nice check, but it's just absolutely not necessary. All right, so E, finally going to do some calculus here. So we're going to take the derivative, and the derivative of this one is going to be 3x squared minus 1. And so we want to know, where is this thing 0, and where is this thing going to be DNE. So the 0, reasonable enough, so we're going to say x squared is equal to 1 over 3, which means that x is equal to the plus or minus the square root of 1 over 3. Now, depending, you may wish to tidy that up a little more. So it's plus or minus root 3 over 3. Doesn't really matter. I probably wouldn't be too picky about that. Next up, the DNE part. This doesn't give us any DNEs. It's going to be solvable. It's a quadratic, so its domain is everywhere. It doesn't not exist somewhere, so that's not going to be something that we bump into for this particular question. So now that I've found these critical numbers, we're going to evaluate what happens in between these critical numbers. So I have negative root 3 over 3, and I have positive root 3 over 3. So I want to test values that are for sure on this interval, and this interval. So if I test values on the first interval, I have to make sure they're less than root 3 over 3. Now, root 3 is going to be smaller than 3, so this is a number that's closer to 0 than negative 1. So I could use negative 1, for instance. So I'm going to. And what am I testing? I'm testing to see the sign of the first derivative. 1, that's what would tell me about first derivative test on each one of those intervals around my critical numbers. 2, knowing what the sign of my first derivative is going to tell me whether my function is increasing or decreasing on that interval. The only opportunities my function will have to switch between decreasing and increasing is if it goes through 0 or if it does not exist for a moment and switches on the other side. So we have written down on this number line all of the possible locations where either one of those situations could occur. So on the first one, negative 1, again, I'm looking up at the first derivative. So that first derivative is going to end up being evaluated at negative. So I mean, I could put it in here. We're evaluating this at negative 1. And it doesn't even matter what the number is. It matters what the sign is. So I'm going to get negative 1 squared is 1. 3 times 1 minus 1 is going to be positive 2. So I'm going to put that as positive here. So I get a positive first derivative. In between, the nicest number in between those two values would be 0. So I'll put a 0 into it. It's going to be 3 times 0 squared minus 1 is negative 1, which is going to give me that f prime at 0 is going to be negative. So we get negative on that one. F prime at positive 1 is what I'm going to test for the third one, and that's going to be, again, 3 times 1 squared minus 1 is 2. So we'll have positive value. So that is going to be positive on that interval. So what this ends up telling me is that I have found that the original function, not the derivative. So every time that we're actually discovering something, we are discovering this so we can describe what the original function does. So in this case, the original function is going to be, so f of x is increasing. I'm going to say, well, on is probably more the, so on, x is an element of, I'm just going to use interval notation. So x is an element of negative infinity to negative root 3 over 3 in union with root 3 over 3 to positive infinity. And then f of x, the original function, is decreasing on x is an element from, and then it's in between those two. So it's negative root 3 over 3 to positive root 3 over 3. And I gave myself no room there. Apologies for that. All right. So that is the end of finding intervals of increase and decrease. Next up, find local absolute maximum minimum values. Okay, so they can occur at our critical numbers that we found. So the DNEs or the zeros, of which there were only 2, then they're both zeros. What was happening at both those, they are both stationary points, which means the derivative is 0. So you have 3 options. You have either a local max, a local minimum, or neither, which we'll usually call a saddle point. In this particular case, though, we transition from increasing to decreasing and decreasing to increasing. So slopes that go up to slopes that go down, slopes that go down to slopes that go up. That looks an awful lot like a maximum, and that looks like a minimum, and that's actually true. So we would be able to say that at the negative root 3 over 3 value, there is a local max at negative root 3 over 3, comma, and then the y value, since we're, as I said before, we're always finding out information about the original function, the original graph. So when I actually try to find out what the point is on the original graph that's local maximum, I want to take that negative root 3 over 3 and place it into my original function. My original function is that thing cubed minus itself. So that's kind of a gross number, but it's going to be negative root 3 over 3 cubed minus negative root 3 over 3. So it's just plus root 3 over 3. So I'll put it like that. It's I could say that that's the same thing as like 3 root 3 over 27, and I guess it reduces, so it'd be like root 3 over 9 or something like that, and the negative would be there. But it's just kind of playing around with it. We'll graph it afterwards and see what that looks like. So the local minimum, I guess what step are we on? I didn't label it this time. We're on F. And yeah, I did label E. All right, so local minimum at, and then this would be the root 3 over 3, and then same thing, root 3 over 3 cubed minus root 3 over 3. So, just to double check, yeah, there was the maximum first, the minimum second. So there we go. We have our local maxes and mins, and they, because it's a cubic, we probably know that there's no absolute maxes or mins. I'm okay with just not stating it. You don't have to say there is no absolute max or min. Just if there is one, mentioning that it's an absolute is nice. So next up, we're going to find concavity. So in order to find concavity, we take the first derivative that we already have, which is going to be 3x squared minus 1. So I'll just rewrite that here. 3x squared minus 1. And then I'm going to take the derivative of that, which gives me 6x. Now, looking to see where this thing does not exist, or 0. So does not exist is not going to be an option. That's the 6x. That's just a nice linear function. But this thing does actually have a 0 at 0. So what that means is, if we were to describe this again using a number line, and we're kind of assessing how's the behavior of the second derivative going here, the behavior has a chance of switching at 0. So the second derivative can switch when the second derivative is 0, or when the second derivative does not exist. In this case, just the 0. And so I need a test value that occurs before 0, and a test value that occurs after 0. Again, negative 1 and 1 probably make the most sense. They're the tidiest small numbers on either side. So if I test a negative 1 in here, we'd have second derivative. 6 times negative 1, which would give me a negative value. And the second derivative, if we test the positive 1 in there, it gives us a positive value. So negative over here, positive over here. What does that end up meaning? Second derivative being negative is what we discussed earlier as being concave down. So this is the original function is concave down. I'm okay with just saying CD or CU. So it's concave down on x, which is an element from negative infinity to 0. I should mention this. Non-inclusive because the zeros don't count as positive or negative. So round brackets on both sides. So f of x is concave up on x is an element from 0 to infinity. So the idea there is that we have a concave up function for the second part, concave down function for the first part, which means that there is a change in concavity that occurs at 0. So we're going to use that when we go to describe a point of inflection, which we already basically have shown where we could have points of inflection by finding the zeros or d and e's of the second derivative. But since we do transition between negative and positive here, that actually is a POI or a point of inflection. So we can say that POI at 0, and this is again a point on the original graph. So I'm going to be thinking of what is my original function. Well, it's x cubed minus x. So x cubed minus x is going to be 0 cubed minus 0 is 0. So we have a point of inflection at 0, 0. All right, so we are done finding information. It's a lot of information to find. Let's talk about what it means in terms of graphing. So I'm just going to get a little coordinate axis here, and let's put down some points. So if I were to I'll back up, and anything that is a point, just realized my, it doesn't really matter, but my, yeah, it's not quite right angle there, but that's okay. So I have a 0, 0. That is a point of inflection, and I'll think about how to draw that properly in a moment, but it is an important point that I have. Now, these ones are a little bit crappier because if I'm actually graphing now and I don't just care about expressing them as some sort of exact value, then root 3 over 3 is, I mean, it's fine, but it's not going to be all that much helpful. So let's see here. I'll bring up the calculator for a second. And we'll just pull it over. Whoa. And so root 3 over 3. And we get 0.577. So that's going to be the x value that's associated with that, about 0.58. So if I were doing this and saying that this was -1, then it would be a little bit over the halfway point. So this would +1 up here, we'll say. Those aren't really points, those are just the grid lines there. And let's let's go ahead and assess what the other number would be there, which it is this value cubed minus this value, or the negative. I'm going to do the positive one, even though that's kind of on the wrong side of things. No, you know what? I shouldn't. So I'm going to do the negative, and I'm going to cube it, which... Oh, this is going to be really lazy. Let's just do it as 0.58 negative, and then times 0.58 times 0.58. Yeah, this is the best way to do this ever. And then that's the negative, and then we're going to add plus 0.58. All right, so it's going to be at 0.38. So if I do about the same thing, and I say that scaled this way, that's going to be +1, that's going to be -1. So we were at -0.58, which is somewhere around here probably overall. So past halfway when we're going back to the left, and it's going to be less than halfway at 0.38 when going up. Now, I could be really, I could go through that process again, but this is an odd function, which means that at exactly the same distance away from my y-axis, I'm going to find that it is the reflection of it. So if I reflect this point across the y-axis and then down across the x-axis, it goes to my new point that I just drew in, and both those should be okay. So this one is supposed to be a local max, and this one's supposed to be a local min. If I back up the truck here to local maxes and local mins, yep, that's what that looked like. And so I have a local max there, a local min there. I also have an intercept here and an intercept here. Now, again, I could label, I just haven't given myself enough space, but I should probably be labeling all of these points, especially the ones here and here, because they're a little dicey. So if I said that this was root 3 over 3, comma, and then root 3 over 3 cubed minus root 3 over 3, and I could do a similar thing up here. All right, so we have pretty much all the stuff we need. Now, all the important points. We should be able to draw the right pieces between them. So what we need to know is it increasing or decreasing? And is it concave up or concave down? The switch between concave up and concave down happens here. This is our point of inflection at 0, 0. So it's concave down, and then we hit a local minimum. Oh, sorry, concave, my apologies, that is not concave down, that's concave up. I was curving it the right way, but I said the wrong thing. So this is actually concave up. So it starts going down because it's decreasing. But what ends up happening is because the change is positive, it's concave up, those decreases get smaller as you go along. They flatten out to become your local minimum, and then they become larger on the other side. Because this is a point of inflection on the other side, we are curving down like an unhappy face, and that's our local maximum right there. And then we curve down still like this because it's concave down that entire time. And so if we were to test our intervals of increase or decrease, we said that the interval of increase was from the negative infinity to this point here, which it looks good. And then, so I'll highlight that with a different color. So to this point here, that would be our first interval of increase. And then we have another interval of increase over here, which was from this local minimum further. So that looks great too. And then in the middle, we had our interval of decrease, which also looks great. And then if we, again, state our concave up, we said that it was from 0 to infinity for concave up, and it's from 0 to negative infinity for concave down. Both of those look great. So the first one was a happy face, the second one was an unhappy face, and that is graphing a very simple function by using a very large process. So welcome to graphing functions. You're gonna love it. Each of your examples is gonna take a long time, but you need to basically pick through them carefully. Do the best job that you can, and see how it goes. So just to see how I did, see if I have this set up right. So I am going to, not that this one's a real surprise function, but we'll go ahead and look at my graph versus theirs. So here's Desmos. It's pretty similar shape, but not only the similar shape, this point right here, we said was negative 0.58 when I rounded it, when I said it out loud, and again the other one was about 0.38. Now this is 0.384, so it rounds down technically, but it's pretty close to right in smack in the middle of 0.38 to 0.39. Anyway, so we got that point right, and we even expressed it using exact values with roots if we wanted to be really picky about it. That one looks good. It definitely has this nice concave down shape, unhappy, but then somewhere along the way it flips, because over here is happy. Where does it flip? It flips at the point of inflection, which was 0, 0 for this particular problem. All right, so this is a long one. Hopefully you stuck around, and well, if you did, congratulations. Give yourself a pat on the back. I'm going to do, obviously, because it is just, your attention span probably doesn't want to kick around any longer, even if you did make it this far. I'll do another example or two later on this week that are a little nastier, and your assignment is basically going to be just to do probably 2 or 3 of these, and that will be it. So I hope you're doing well. Thinking of you. If you're visiting the school this week, all the best. And if you're visiting it Thursday, mate, see ya. Take care.